again. Alright, topic 3 now is random matrix theory. This is one of my personal favorites. I actually learned number theory as an undergraduate at Yale from Professor Firk, who was a nuclear physicist. He was one of the original experimenters doing stuff like this, and he was frustrated over the paucity of data in nuclear physics. And it turns out the same mathematics describes the Riemann zeta function and a whole slew of other things. And so I've done a lot of work over years in random matrix theory. What I want to do is briefly describe what it's like, why it's useful, and what kinds of problems you can look at. So I need to discuss a little physics. So imagine a universe where the only force is gravity, and there's only one point particle. It is not that hard to describe what happens. If there are just 2-point particles in the universe, it's not that bad. If there are 3-point particles, you can't just say by induction everything is fine. We can no longer write down a closed-form analytic solution with 3-point particles in general configuration. This is what Poincaré wrote his classic paper on. This is what got him the prize. This is where, in some sense, chaos theory really was first discovered. So imagine now you have uranium. If you have any, please let me know. We have over 200 protons or neutrons with a very complicated force of interaction. And you want to understand the energy levels of uranium. If we can't even do 3-point particles under gravity, how are we going to do something like uranium? Now, there are things we can do. We can shoot neutrons into the nucleus, see what happens, and get some information. So we have an experimental understanding, but we would like a theoretical one. Well, in quantum mechanics, you learn that you can model your system like this. So H is your Hamiltonian. It's the operator attached to your system. En is the eigenvalues, and Cn is the energy eigenfunction. So all we have to do is solve this linear algebra problem, and we know the energy levels. There are only 2 issues. The first issue is that H is infinite by infinite, and the second issue is we don't know any of its entries. So it's fairly tough to diagonalize an infinite by infinite matrix if I don't even tell you one entry. And so Wigner's great insight was to say, well, okay, let's approximate. Let's imagine I have a large n by n matrix. And maybe because of physical grounds, my matrix has to be real symmetric or complex Hermitian. I'll fix some probability distribution P. So P is a probability distribution. So it's P of x is greater than or equal to 0. The integral of P of x dx equals 1. And what I'll do is I will choose each independent entry of my matrix independently from this probability distribution. So for instance, if I have a 2x2 real symmetric matrix, I choose this entry from my distribution, I choose this entry from my distribution, I choose this entry from my distribution, and then this entry is forced on me. So I can put a measure, a probability measure, on the space of matrices. For each matrix that's n by n, I calculate its eigenvalues, and I look at their properties. I then average over all such matrices. And the idea is the behavior of a typical matrix should be very close to the system average. So if you want another example of this, let's say you want to calculate the pressure in this room. One way to do this is to look where every single molecule is in this room, see where it's going, see what its speed is, and then see exactly how many will hit this blackboard in a small amount of time. This is computationally infeasible. Right? There will be at least several moles of molecules in this room. We're not going to be able to write down something like that. But what we could do is say, well, let's consider all possible configurations of air molecules. For each configuration, we can calculate the pressure and average over them. If you have enough things to average over, you can actually do these calculations. So in the simple case, each air molecule is maybe either moving left or right. And I want to know just how many air molecules are in this half of the room. So using the central limit theorem, we can get very good answers to questions like this. And then with very high probability, the configuration of air molecules in this room will be very close to the system average. The same thing happens here. For these random matrix problems, we can actually calculate these averages over the entire system. Now what we want to understand is the eigenvalues of the matrix. What we understand are the matrix elements. So the most important result for us from linear algebra is the eigenvalue trace lemma. So the eigenvalue trace lemma. And what it basically says is the trace of a to the k is the sum of the eigenvalues of a to the kth power. This is very similar to the transfer principle we saw with the Riemann zeta function. I want to understand the eigenvalues. I understand the matrix elements. This connects the two. And the way you should think about why this is useful is, in some sense, this is giving me the kth moment of the eigenvalues. So if I give you a probability distribution, if I integrate x to the k against that, we call this the kth moment of the distribution. This is kind of analogous to a Taylor series expansion. And for those of you who have taken complex analysis, you now know that Taylor series expansions are not unique. But if your function is nice, then the Taylor series expansion should uniquely determine the function. Just like the moments should uniquely determine the distribution. And so by understanding all the moments of my eigenvalues, I should then understand the eigenvalues themselves. And so this is the idea that's going on here. The question then becomes, all right, then we have to weight each of these by the probability that we took our matrix A, then we integrate over the space of all matrices. We deal with stuff like this. This is going to be a polynomial in the matrix elements. It turns out using combinatorics, we can actually evaluate this. And so for years I've had undergraduates working on various matrix ensembles. There's lots of great problems here. But the actual answers you get are going to depend on the structure of your matrix. If your matrix is full real symmetric, you get one combinatorics. If the matrix is constant along diagonals, you get another. You can apply this to more than just random matrix theory to model nuclear physics. The answers you get here also describe the zeros of L functions. We have some idea why this is true. In what's called the function field case, we know what's going on. In the number field case, like the Riemann zeta function, we don't know exactly why, but we have some reason to believe that this should be a good connection. And so it's phenomenal that you can see the same behavior in two very different systems for very different reasons. Okay. There's lots of other things related to random matrix theory, random graphs and whatnot, but in the interest of time, I'm going to just leave it as here, and you can skim the book if this looks interesting. Any other questions on